I would just like them. But let's give them enough road, as my mama says.
Yeah.
Did you hear about the shooting in Vegas? Oh. I just turned the radio off. I'm a, I've been connected this weekend all, but on the way to work this morning, shooting at a concert in Vegas, and there's 50 people dead and they expect more. Hundreds wounded. And so they're just now starting to release details, and it was all ignorant stuff. Oh, I've heard this. It happened last night in concert in Vegas, and I think they're about 3 hours behind us.
What's the there?
I don't know. Pray and pray hard. Now, 2 weeks from today is when I have to be in Cary, and I'll be gone Monday and Tuesday of that week. Jim's Jim knows, and he's true. Oh man.
Yeah, so okay, so what did I originally have?
She don't know me. She know me.
Hey, Razor.
For us,
Look at that.
but
You got the same
that
thing?
and
What did we do? We didn't put arrows.
if I show that, they will see
Arrows.
there on us. They will see. They have 2 monitors. They'll see that in your screen.
I didn't put T equals 0 and he got mad at me.
Video captures both simultaneously. window smaller, and so you have a dual foot view.
Oh well. Nothing to be done about it now.
Yeah.
Yeah, sweet Asian chick, she was
Joe, have you looked at Raspberry Pi? It's way cool, not that expensive. You want to put your program
I make E4 checks.
operating system. I think
Typically,
that
it'd be really
Pi
disappointed,
is
but I'm
out
not
of Java. So if you want to do that, it's an inexpensive way to start looking at device programming. I don't know if you're interested in device programming or database programming, whatever your area is going to be. I didn't see.
So I know what a tangent line looks like on the graph, but how would you find
You go up to the unit. But instead of pi is
on
so it would be, but if you have that, you get start units programming.
So if you took the derivative of like a quadratic equation and you got a linear equation with a positive slope.
Did you have a point?
A point?
Yeah.
Like a point on the line.
Oh, the point where they intersect?
So like if it's like at x equals 3, then you plug 3 into the function and get the y value and you have a point. Now you have a point and a slope if you just find y equals mx plus 2.
Wait, so would the slope of, would the line of a tangent be perpendicular to the line of a secant? No. Okay.
Yeah, I don't know what that is. Is that a whole different line?
Stand looking
secant
like a
line?
British
No, when he
EDM
asked for the
musician.
normal perpendicular.
Hey guys, Skrillex here.
Perpendicular just means it has
Quarter.
the opposite reciprocal slope of the tangent.
We got this crap back.
Yeah,
It's
so
like-
why would we need that?
Yeah. It's soup.
I think for right now it's just a secret.
Got a sweet
get it,
Asian chick,
so-
she go low man.
How do you
Low man.
I found the equation of the derivative, but I couldn't find it on the
just
tangent line. I kept getting a single number.
Yeah, I saw
So like, I got
this.
this tangent line. What number did you find it on?
You hate a child. His fan base hated on him.
Like on the first,
Like, why
on
do
what?
you not like the music
Giant
video?
horn?
You just
No,
shout.
the lab.
Not a child. You know what I'm saying?
Okay.
It's number 10 on that one.
Yeah,
For the first function, I got
guy.
it.
We just flamed him for it.
So
For
you're
what?
gonna plug in 2
I
into
mean,
the
of course,
function
Etika's fan base isn't.
That's what I got for
and get a
the,
y value.
Am I right?
So you have
Of
2
course they
comma whatever it
Yeah.
is. And then once you find the slope,
X,
right,
So
the derivative, once you find
you
the
know that
derivative,
X is
you
on.
have the slope of the line.
We don't know. I mean, we can assume, but we don't know.
Then you
don't
are
think
gonna
he
find
is?
a perpendicular line to
Why?
that, so to have the opposite reciprocal.
so
We
you would
seen
take
him.
the,
Yeah. I don't know though.
so the tangent line would be the perpendicular form of the secant that has that point in it, or?
I put a
Like
whole-
where, how would you,
Perpendicular line is completely different than.
but how would you get
For
the
real,
slope?
that's what his line.
Like I plugged in
pound
the point
Straight
2
to the
into
booth.
that and I got the point 2
But yeah,
So
you
what
were
would I do
you were
with that
wild
point? Like,
at
how
the
would I get
beginning
the
of the
slope
music
of
video, and then you're just talking about police brutality.
The
Systemic
slope of the
oppression.
tangent line is that.
Actually, I like the scene.
Yeah, I mean it's a really cool music video. I just don't know why he did it. It should have been too.
So would it be the
He just did it
exact
for
same
shock,
equation?
shock for the sake of shock. There was no benefit into making it the music video for it.
It'll be an X, basically.
X.
Okay. Let me try this.
Hey, can't keep up. Come up. I'm like, who was your name? Mommy, don't love me no more. I gave him, she got me. I can't even say what.
No, I didn't do
Yeah,
any of it.
just about a pound of the
Number
booth.
1 and then
I
number
thought straight to the booth. That's a good line, by the way.
Yeah.
I mean, a lot of that. He has really good bars. He can keep a flow. It's pretty impressive. Yeah, but he's X, so he's just garbage. Is it worth taking off the cardigan?
No.
We'll see how warm it'll get.
It's changed.
Yeah, man. Is that Mr. Gaddis? That's what I live for.
So for number 10 on the first equation, I got y equals negative 1/2 x plus 2. Is that what everyone else got?
So your slope is -1/2, the slope of the tangent line, or the slope of the perpendicular?
The slope of the tangent
I
line.
think it's one.
I
Yeah,
thought it was
2x minus.
yeah, I'm pretty sure it's one, Sammy.
Huh?
I'm pretty sure it's one.
I messed up.
What's 1?
The
slope
slope
is
is 1.
Yeah.
I got the equation of y.
Well, I got
equals
y
x
equals
minus
1,
3.
but I didn't
Yeah.
know what to do with the y. Wouldn't you plug it into the equation then?
I'm pretty sure it's one. The slope is one.
You want to see my English percentage if it'll help at all?
One.
I'm expecting any of mine to be right. I just
Well,
know
I
my
didn't even-
derivatives are right. I just know my derivatives are right. That's all I know.
Just bought a pound of the booth. Bought that straight to the booth.
I don't think we did it.
Well, screw Carson. I forgot Carson was a person. He just said his name. He suddenly remembered he existed.
Yeah, pretty forgettable.
Yeah, what a forgettable dude. Math God is irrelevant now. We're atheists. Is that printing tape? No, it's not printing tape. It's the farthest thing from printing tape possible.
That's so weird.
Oh, it's true. It's true.
That doesn't mean it's nice.
I don't think it's mean either.
Yeah, I wouldn't necessarily call it mean. It's just an observation.
Yeah. No, that's Brittany's mom. Tracy Tate. Tracy. Dr. Bud. Got a whole lot to it.
Miranda,
Yes,
did you get the percent?
Think some
yes. I've given them out to the people that are here.
Okay, fantastic.
They're up there, sorry.
I
I let them get it themselves, actually.
Wait, what do we get? What?
Get your test back.
Get your whole stack.
Okay, you have it. Yeah,
Wait, what is this?
Correction.
Oh yeah. You think wait, you
No,
didn't turn it
or-
in?
no,
Come
You turned your
Mason,
in.
it's right there.
Up there.
Ian.
why?
Get the stack of stuff, Josh. It's
All
all
of
yours.
it's mine?
Yes, it's your originals and the scanned graded version.
Okay.
Warren thinks I'm stupid or you think he just plays along?
Carson, grab your paper while you're up there.
Actually, yeah, of course, my grades are awesome.
Both of them.
I'm wrecking that class.
I'm doing
I don't
worse
know.
than I should be.
I don't know why people do that class. This is stuff we learned in middle school.
Why? You think I learned this stuff in middle
I
school?
mean, they taught it. I just have good retention.
This?
If it's so
Derivatives?
easy, you
No, I'm
guys should
talking
come take
about,
general chemistry with Mr. Lou.
I was like, wow. I was not once, and not signing
You
up
didn't
for
even
anything
do the
again.
class. You got a nasty email and you were quitting.
Yes,
You can't do that.
can't do that.
Yeah, geez, Mason.
You wimped out.
Didn't even say it.
You wimped out on me. That class is insane.
Does
I
this
got a
campus
70
mainly
on a
just
quiz and he
provide,
was
like, liberal arts
You're
classes?
making a B if you made a 70. That's so
Yes, sir.
good.
Is that just mostly what they do here? Just liberal arts classes? Yeah.
Yeah, the AA Arts Associates and
Where do you
Why? It's just calculus and learning.
Oh, I need my book.
Actually, I think DCCC is more medical oriented.
It's like that.
Like you have a lot of nursing programs and stuff.
It's not more application based.
Just bought a pound of the booth. Brought this straight to the booth. Thanks, man. I'll shower it now, so I don't have to take mine out.
Like a 90-year-old man. Give me your jacket.
Just bought
Once
a
we
pound
leave
of
the room.
You can put it on
No,
right
once
now.
we leave the room.
Well, actually, it's gonna be cold though. That's when I'm gonna want to wear it.
So let's go ahead and get started, I guess. It looks like the dates are missing. Dylan, Sydney, Elise,
He's a traitor. He left the alliance.
Okay, so you should have back your test work questions and the lab. I want to talk about the lab for just a minute. So I'm going to let's share this. I posted on Moodle a copy of a solution sheet I've written for the lab, so you can check it out. I just want to point out so it's on Moodle. This is the lab you were given, and I went in as part of my solution work. As you observe right here, time.
Okay.
0, 3, and 5. I put a time where something key happened, like here at the bottom of this curve. On problem number 5, notice I put time numbers when something key happens, like 1.5 at that key, 4 at this bottom, but also put 2.5 right there. 2.5. A lot of us feel that very clearly. Why is 2.5? Why is that a critical number? I mean, it's obvious 1.5 is critical. Something changes there drastically, and at 4 something drastic changes. But what's different at 2.5? Well, I can't really follow this. Did y'all see? Is it zoomed in enough that you can see that? Why is 2.5 the important time value right there on that picture? Problem 5. Are y'all with me?
Because it's an inflection point.
Oh yeah, suggestion why that's critical. Yeah, it changes from on the first part before 2.5, your curve is going up and then back down. It's curving like that. That would be in a way that your velocity is decreasing the whole time. Velocity was up, we got less up, velocity got flat, the velocity got steeper and steeper. So the velocity is decreasing the whole time as you're going to cross that crown. But then after 2.5, what happens? Your steepest negative velocity, then that negative velocity starts to shallow out. That means it's increasing. Now it's 0. Now it's positive. So at 2.5 is where your velocity changes, and decreasing in velocity, decelerating, and then after that you're accelerating. And then there was one other one that was important that way. Maybe it's not it. 9 is not a problem. 11 was it was important to identify that something happened there at 2.5 or somewhere. I mean, if you didn't use the exact same numbers, you could have used 3 or whatever. But something definitely changed right there at 2.5. What changed? Why is that important? I mean, that's a nice straight line, but why is it important at 2.5?
That was velocity change.
Yeah, that's where velocity 0 changes from positive to negative. Is that right? The hardest one was number 12. So let's take a look at it for that. Okay, so here's number 12. Again, the time values that you used didn't have to be exactly the same time values that I used, but you did need to break it up into these intervals. Clearly, something's happening at 1. The velocity's gotten higher, 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 and then the velocity kind of peaks out at 1, time 1, and then velocity starts to kind of come down, gets 0 at time, I'm calling it time 2. When the velocity is negative, it gets the most negative it's going to be at time 3. And at time velocity starts to increase up to a 0 velocity at time 4. Then velocity goes up and it increases for a while. And I put time 4.2 just because I used a 4 there. So then from 4.2 across to 5, what do you notice about the velocity? It's not increasing anymore, is it? It's constant. And that changes how you answer the problem distinctly. So if we scroll down here, I have the answer right now. It's advancing on, I think everyone got that correct. Whenever your velocity is positive, it's advancing. So it's advancing, even including that flat part at the end, it's still right here, the 5, that's still advancing. And then it's retreating the other rest where it's the velocity function is below the axis. But it's not accelerating out to 5. Okay? It's no longer accelerating out to 5. It's also, you're not speeding up out to 5 either. It's stopping at that point where the velocity turns constant. You're no longer speeding up. So that was something that a lot of people missed right here, this issue. So just be careful. Also, when you draw your graph, one-dimensional graph, notice this is something a lot of people didn't do, but I put not only time values when it turned around, like here, time 2, and time 4, I put those in, but I also put time values in the middle where things change. Notice, like at time 1, on the left side of time 1, velocity is pointing to the right, and the acceleration is pointing to the right. But after time 1, but before time 2, velocity is still pointing right, but acceleration is pointing left. So every time something changes like that, I put a time value. Even if the direction, my velocity is still going to the right, so I'm still moving to the right, but my acceleration changed. Here, my velocity is left, and still left, but my acceleration changed. So every time something like that changes, you got to put a demarcation indication. Notice after time 4.2, I didn't show any acceleration because there wasn't. There was a constant velocity. Okay, so be a little careful of that. I mean, it's only 1 point for your graph, so it's not that big of this. Be careful going forward. Questions? This is online, so on Moodle. So go home and take a look at it more detail. So I've got all of the, zoom back out a little bit. I've got all of them, what the answers are, what the graph should look like all the way down through there. Okay. Other questions we have? I guess you have a lab that needs to be turned in now as well. So make sure your name is on that, and you'll set.
Somebody do a picture.
Yeah.
Take it off your little test paper there. Hold on, you want?
I just gave you.
Where did the links go? You just turned it in.
Yeah, I want to go over number 6 on this. Just a number 6.
I gotta take these off.
I'm so tired. I slept in my
Oh wow, lucky you.
No.
I didn't get to sleep at all.
To get here. Why?
Because I woke up in the middle of the night thinking about Pennywise.
Did you watch the movie?
No. I just woke up thinking about like Pennywise and Bloody Mary, and I couldn't go back to bed. So. What? Yeah, I woke up thinking about that X. That was awful. I'm gonna get a wink sleep after that.
I should have thought of it. Sam, I didn't think we were turning these in.
I didn't sleep until 2.
I don't understand why they called that.
I screwed up so bad. Brittany. I screwed up so bad.
What did you do? Okay, I'm just gonna go over.
Okay.
People.
Yeah.
Oh. We got more people here now.
We're at the bottom.
Here. Is Elise here yet?
No,
Oh.
No, I do.
He came in on time.
Right.
Okay, let's,
Because I wouldn't have
we need to discuss section 2.2. Before we start on that, I'll just ask the general, any like questions that just burning in your mind before we get on 2.2, but positive constipation and whatnot, lack of sleep. There's everything. Got a whole course. Well, if we weren't losing sleep over math, then we're not really doing our job right. That's what my professor said. So, let's start by going over problem 1 of section 2.2, true false, and discussing it. Hopefully that wasn't too bad. Then we need to kind of get into some of the details of the section and make sure we're clear on it. And there's a good bit in this section, so we need to. So we'll start with, again, problem 1, see how we're doing. If we had a chance to look at it and try it. If not, try anyways, and we'll learn from our mistakes. Okay, so 1A, want to volunteer to start? Raise his hand up first, we'll go with Rayla.
All right, number 1A, true or false? F prime of x is equal to f of x plus h minus f of x over h. And I said that's true by definition 2.2 in the section on page 170, which is the derivative of a function.
Sammy, you have your hand up?
I got false because on page 170 it says it has to be the limit as h approaches 0 and then that equation.
I agree with you, Sammy, that it is false because they sneakily left out limit h approaches 0 on that. So the difference being, one more time, with the limit h approaches 0, you're taking two distinct points and shrinking them close to 0, close together, so that you get the tangent slope. Without the limit, what do you have? What's actually shown on the right side of that equal sign? You have the secant slope actually shown on the right-hand side because you've got two distinct points there, a distance of h apart, and that gives you the secant slope. So I agree, Singer. Good. 1B. Jason, you had your hand up?
Okay. True or false, f prime of x is equal to the limit of f of x plus h minus f of x over h as x approaches 0. And I said this is false. It needs to be as h approaches 0.
I agree with you there. As h approaches 0. Good. Good. Number C. Go ahead, is his hand up?
Prime equals the limit of c minus x over c minus x, c should be a z.
Correct. Should be z approaches x to be the definition of derivative in that form. There's, again, they wrote it in two different forms. The form that we normally use is the one with h approaches 0. The other form is z approaches x, and that's kind of showing the idea of 2 points getting close together by literally moving 1 point to the other point. H approaches 0 is the same idea, but h is the distance between the 2 points that you're shrinking to 0. So it's achieving the same goal, but a little bit different writing. But you're absolutely right, Joe. That's false. How about 1B? Jake?
True or false? If f of x equals x cubed, then f x plus h equals x cubed plus h. I think that's false. It's supposed to be x plus h.
Yeah, it's supposed to be the quantity x plus h cubed, which is not x cubed plus h. It's not even x cubed plus h cubed. right? The quantity of x plus h, quantity x plus h cubed is not equal to x cubed plus h. Okay, and certainly not x cubed plus h. How about E? A volunteer? Carson, you take it?
Yeah. True or false? If f of x equals x cubed, then f prime of x equals limit as h approaches 0, f parenthesis x to the third plus h minus f of x over h. And that's false because the second f of x should be x cubed, and it's just not. It's f of x.
Well, on E, I think the issue should be that the first x cubed, where it says f of x cubed plus h, that should simply say f of x plus h. Because the f function does the cubing for you. You don't put the cube on the x, the f does. So if you take off the cube inside the parentheses on the first term, it would be correct, I believe. Be correct. Okay? So I agree it's false, but it's false because the x cubed should be steps. How about F? Josh, could you take it?
Yeah. True or false? A function f is differentiable at x equals 0 if and only if f of c from the left and f prime of c from the left and f prime of c from the right both exist. I said this was false because of definition 2.3 of differentiable.
Okay. Yes. If the left differentiable, if it was left differentiable and right differentiable, and they both were the same number, then it would be differentiable at C. It's like limit. It's going back to the idea of limits. You can have a limit from the left. You can have a limit from the right. The overall limit only exists if they're the same number. Well, in derivative, it's the same idea. We can have differentiability from the left. We can have it from the right. But the only way you can have differentiability at the point is if those two numbers, those two derivatives, are the same. So G, Adam? Yes, so how can you give me an example when it would be false? It's continuous but not differential. I agree with you. That's absolutely true. You said it's false. So a function that has a sharp corner on it, sharp corner, not a smooth curve, will be continuous but not differentiable. Do we understand why? I'm going to go right here on this. So if I draw some function with a sharp corner on it, like that, then at this point C right here, if that's C, we would certainly say that since the two sides meet and there's a solid dot there, then certainly f of x is continuous at x equals c. But what about differentiable? Well, tangent lines on this side, draw little tangent lines. What limit value do the tangent lines seem to approach as you get close to C? Just the tangent lines. They all seem to be getting close to, say, 1 or something like that, whatever. So f prime from the left at C seems to be kind of like, I'll call it positive 1. And then if you approach from the right side, so your tangent lines on the right side all seem to be a negative slope of some sort. So if I'm going along happy with a positive 1 slope, then suddenly I'm at a negative 1 slope, how do I have a tangent line right here on this point? I mean, how do I suddenly change from a slope of 1 to a slope of negative 1? You don't. Not easily anyways. So we would say it's not differentiable because of this. Those aren't equal. Then we would say the derivative at C it does not exist. So left side and right side do exist, but they're not the same number. And so it is continuous, but it's not differentiable. The theorem says in the book, if it's differentiable, then it's continuous. So differentiability guarantees that it's continuous. But continuity doesn't guarantee differentiability. On the other hand, if it's not continuous, then it's definitely not differentiable. And you can draw any picture you want for that. You have some curve like this, and then some gap in it. And that's pretty obviously not differentiable at C now for the same type of reasoning, only worse. I mean, my slopes here are positive, getting more and more positive, and then all of a sudden they jump up here negative, so that can't happen. So if you have discontinuity, you definitely will not have differentiability. If you have continuity, you might have differentiability. And then H, Brittany, can you take H for us, please?
Yeah. True or false? If f is not continuous at x equals c, then f is not differentiable at x equals c. And that's true because of what we just said.
That's true because that's called the composite of the theorem that they stated on page 172, the differentiability parts. Okay, good. Well, let's make sure we're clear on all the content in here. So you've got the definition of derivative at a point and as a function. What's the distinction there? Over here. Derivative at a point. That's the limit x approaches 0 of f of c plus h minus f of c divided by h. So that's at a point, but if you have a function, have the limit x approaches 0, excuse me, not x, come on now, h approaches 0, f of x plus h minus f of x over h. Those are the definitions for at a point and at a function. So we would call this is f prime at c, and this is f prime at x. Okay. My thinking is, in general, I'm going to do it as a function, because after the fact, as you saw in your lab, once you create the derivative function with a variable x in it, I can plug any c number I want into this function and get the same result as if I just do the derivative at a point. So why would I do individual points when I can do a function and then use it for any point that I care about? We just talked about left and right differentiability. The definitions are in there as well. You're approaching on one side of 0 or the other. So if I wanted to put left or right differentiability at a point, so if I wanted to call this, for example, we'll just put some coloring. Let's call this differentiability from the right side. If I was going to do that, what would I have to change this definition to call it differentiability at that point on the right side?
Would you purchase 0 from the right?
Right side, that's right. Good. But what about going to call it differentiability from the left side? What would I have to change?
It'd be a left on the 0. Yeah.
So, all the same formula, just either left or right. It's kind of easy, I think. Questions on that?
No.
Okay. Use that to do derivatives of piecewise functions. So let's do one, I guess. I understand what's going on.
It's not in the book. Man. That's fun.
So let's let f of x equal absolute value of x. Which, by the way, has a graph that looks like this. Okay. But if I wanted to take the derivative, if I wanted to find f prime of x, and write it out as a function, how do I do that? You did it on the lab. I gave you a quadratic function, and you had to find the derivative of it. It's not that hard. But when you got absolute value in there, things get a little bit dicier, unless you use the definition of absolute value. Remember what the definition of absolute value is?
Yeah.
So first observation, is this function f of x continuous at x equals 0?
Yes.
Mm.
Yes.
Yeah.
This is approach to 0.
Yeah.
How can we show that? Let's just review that. This is a good quick review. How do I show continuity at x equals 0 for that function? This is going back to last one.
Let's
Well.
solve for the limits as it's approaching 0 from both sides.
Yes. So we'll do the limit x approaches 0 from the left side of f of x. When you're doing the left side, that means I'm smaller than 0, so I'll use this one, which is limit x approaches 0 from the left of negative x. Well, when you get close to 0 and you're taking the negative of it, you're still really close to 0. And then similarly, limit x approaches 0 from the right of f of x equals the limit x approaches 0 from the right of. Now, when we're from the right side of 0, we're bigger than 0, so we use x. And when x gets close to 0 from the right, we're getting really close to 0. And the final step is to show that f of 0. So if I actually plug 0 in the function, plug 0 in, I get a 0 because I used the first definition up there. These three things right here, take all of those together. This shows continuous at x equals 0. Sam is right. You had to look at the left and right side limits. Exactly right.
Mm-hmm.
But those limits not only had to be existing and equal to each other, but they had to equal the function value. Okay? If the two limits exist and are equal, does that guarantee continuity? No, there could be a hole there. So the two sides have to exist, be equal, and equal the point in the middle. So it takes all three things to show continuity. So we've shown continuity. We have a point that is continuous at x equals 0. That's good. Does that guarantee it's differentiable at x equals 0?
No.
So let's look at the derivative and see what that does. Okay. So in order to do the derivative, I'm going to have to do it in pieces, left and right at 0. So I've got something going on the big side of 0, the right side of 0. So let's do that. I'm going to come back and fill this in a moment. I'm going to do the right side derivative. So let's see. Well, whenever I'm to the right of 0, it's always just x. So I'm just doing the limit h approaches 0 from the right of f of x plus h minus f of x over h. But what is x plus h? Let's see, that's f of that, that's just x plus h. So that's x plus h minus x over h. Then h approaches 0 from the right. So x is canceled, I get h is canceled, so I just get limit h approaches 0 from the right of 1, which is just 1. Okay. So whenever I'm bigger than 0, my derivative comes out to be 1 always. So I see that I could write it's 1 as long as x is bigger than 0. I don't know yet what happens at 0. I got to figure that out. So I just looked at right of 0, bigger than 0, and it's always 1. I think it should be easy to see if I approach from the left side. I'm using this definition right here, negative x, and I got to plug x plus h in and then an x. That's going to give me the negative of x plus h minus the negative of x over h. Well, once again, the x is canceled, but I get a negative h over h. So this is the limit. H goes to 0. H goes to 0 from there. Negative 1, which is negative 1. So I have seen that from the left side, the slope is always negative 1. And we should have seen that from back here at the beginning one more time. These slopes on the left side are always negative 1. Those slopes on the right side are always positive 1. I see that right here.
Mm-hmm.
Okay, so m equals 1, m equals negative. Tangent slopes. All right, good. But what about at x equals 0? What happens at x equals 0?
Wow. Does not exist.
Derivative exists.
That's what I said. Just go on.
I couldn't hear what you said. What did it say?
I said does not exist.
I agree, it does not exist. How do you know it does not exist?
Because left and right differentiability are not agreeing with each other.
Correct. Left and right side derivatives, differentiability at point x equals 0 is not matching. So I can't have a derivative at x equals 0. So there's my derivative function for that function. I have a function f of x. I have a derivative function, f prime of x. The graph of this function, what does it look like? If I go over here and graph that function. What's this function look like? As long as you're bigger than x equals bigger than 0, you got a horizontal line of 1. Once you're less than 0, you got a horizontal line at -1. But it doesn't match in the middle, so no derivative at x equals 0. Okay, so that's using left and right differentiabilities to examine a piecewise function.
Mr. Gaddis,
Yes, particularly I looked at absolute value, which is a piecewise function. Yes, right.
can you explain what exactly differentiability is as a trait? What does it mean for something to be differentiable? And it explained in the book, but I don't really get it.
Differentiable essentially means that the derivative expression, this expression here, exists. That when you do this limit,
Yes.
you get an existing real number. If you don't get it, when you do a limit, remember you can get indeterminate. Why do you always get indeterminate when you start off on this game right here?
Because
0 over 0 every time. But if, after you eliminate that indeterminacy, if the limit comes out to a finite real number, then you say the limit exists, and it's differentiable. If that limit comes out to a non-finite real number, as in it comes out to infinity or some other kind of aberration like oscillations or something, then you say the derivative does not exist, so it's not differentiable. Does that make sense now?
Is it just the existence of a derivative? Is that all differentiability is?
Yes, existence of the limit, that is the definition of a derivative. That is correct. That is correct. Okay, next up. Look in your book with me on page 172. I want to discuss along that line of differential that Reza was just asking. Listen, look at these 3 graphs at the top of page 172 for a moment. Go on page 172, see the graphs. Okay, the first graph on the left on page 172, that's basically just what we talked about at the beginning. It's what we just talked about again here. What do you observe? At x equals 2, you have what we call a sharp corner. It's going up and sharp corner going down. At that sharp corner, the derivative does not exist, so it's not differentiable at x equals 2. Again, because the tangent slopes are drastically changing from a positive slope to the left of x equals 2 to a negative slope to the right of -2. And there's no gentle conversion from positive to negative by hitting 0. It's just boom, boom. And that's why you can't draw a tangent line on that sharp corner. It's like, how does it balance on? So it does not exist. But now look at the next 2 graphs. These next 2 graphs we say are not differentiable, meaning the derivative does not exist, but for a different reason. The reason is similar to, think about limits for a minute. If the limit, on just regular limits, not derivatives, go back to regular limits. If the limit on both sides goes to infinity, we said the limit does not exist, but we allowed ourselves to write the limit is equal to infinity. Do y'all remember this? Did we talk about that? Well, for that same thinking, on these last 2 pictures, it is not differentiable at x equals 2 because the derivative does not exist. But the reason it does not exist is the derivative is infinite. So look at the first picture. Look at the slopes on the left-hand side of x equals 2. What do you observe? The slopes are negative and getting more negative. And right at that point at x equals 2, we call that a cusp. So number 1 was called a sharp corner. Number 2 is called a cusp. C-U-S-P, cusp. So it's coming in at a negative slope, more and more negative, so it's vertical slope. And then at the vertical slope at x equals 2, as you continue on, it's still a negative slope and starts to tilt back and come up to less negative. So right at that point, both sides come to an infinite slope. A vertical line is still a legitimate tangent line. It's just that the slope of a vertical line from A to A, the slope of a vertical line is undefined, right? Now with me? So the tangent line is vertical there. There is a vertical tangent line. But since it's vertical, then the slope is undefined. So we said the derivative does not exist. It's not differential. Same thing for number 3, picture 3. Different reason. This is not a cusp. But as you go through that basically is a cube root type of function shape they have there. As you go through that middle part at x equals 2 of the shape, as you're coming from the left-hand side, the slopes are positive. And then it gets vertical right at x equals 2, and then it falls back off again, staying positive. But for a brief moment there, the tangent line becomes vertical right at that point. So once again, because a vertical line has an undefined slope from 8th grade, then we say that the derivative does not exist and it's not differential at x equals 2. Although it does have a tangent line. So that's different. Number 1, there's no tangent line. Picture 1, there's no tangent line at all at that point. You got that sharp corner, there's no tangent line. Number 2 and 3, there is a tangent line on numbers 2 and 3 at x equals 2. But the tangent line is vertical, so the slope is undefined. You see the difference between those cases. All 3 cases, derivative does not exist at x equals 2. One of them is different than the other 2 in a distinct way. Are we clear on this? Everyone there? Sharp corner is different than cusp and simply vertical edge. Okay, good. The equation of a tangent line, you were supposed to do this on your lab. And I hadn't presented that to you. It's in the book, but I was hoping you could figure it out without having to read the book. Meaning, to write the equation of a line, I don't need this theorem in the book. All I got to do is remember my algebra. Write the equation of a line. What do you got to know? We're going to go over here. So from algebra, you write the equation of a line. What are the 2 things you got to know? You need to know a point on the line, and you need to know the slope of the line.
That's wonderful.
Once you've got that, it's easy. You use the point slope form. Y minus y1 equals m times x minus x1. Do y'all remember the point slope form from algebra?
That's y equals mx plus b.
Okay. If I wanted, I could, that's supposed to be y1. Sorry, y1 right there, y1. If I wanted, I could move that y1 to the other side of the equation. So I would get y equals y1 plus m times x minus x1.
Yeah, I don't think I got this. I think I was taught y equals mx plus b.
Never saw point slope form in your life?
No.
Point slope form.
No. I've never seen it.
We possibly have seen it, we just
It
didn't.
wasn't important.
I didn't see it.
Am I thinking of slope intercept form? Is that y equals mx plus b?
You're thinking of a specialized form called slope intercept form.
Okay, so I'm just wrong. Keep on going.
Oh, slope intercept form is a form of the equation. It's just a form that you have to now know the y-intercept in order to use it. The point slope allows you to use any point. See, on yours, you have to know that it's the y-intercept, which means that x has to be 0. x1 has to be 0. But what if x1 happens to be 7? Now what are you going to do? Plus, the point slope form comes from the definition of slope, which is how you generally start with equations of lines. Anyways, so this is the point slope form, and in it we can see a point. So we see a point on the line. That would be right here. So the point on the line is x1, comma y1. But how do you? Well, we'll come back to that. And so from algebra, we see the slope of the line. That's like right there. Okay. So the slope is m. Now from calculus, in calculus, how do we tie all that together? Well, when you have some function curve, this is x1, say. How do I find y1?
Y1.
Y1 is just equal to f of x1. Okay, that was easy. And then, so now I've got my point easily from the function. But the other great thing is that the tangent line is unique in that it is a line that shares one point with the curve. So the point on the line that I need, x1, y1, is in fact the same point as that point on the function curve. So this point on my line right there, this point on the line is also the same point as the point on the function curve, and the slope is easy. The slope of the tangent line is m equals f prime of x. So the book then writes, instead of this, which, you know, I'm good just knowing, if I just know my basic algebra, I can do this and understand that slope is the derivative and a point just comes from the function itself. But the book writes it out something like this. They then put in all the symbols here. They say, well, y1 is just f of x1, and they call it c, I guess. So they let x1 equal c. F of c, then m is the slope at c, so that's just f prime of c, and then x minus c. So they go to all that trouble to write it out. To me, that's an awful lot to have to try to memorize, but I already know how to write equations of lines from algebra. And I need to know from algebra is a point and a slope. And in calculus, we learn how to find the slope. We already knew how to find the point, so it should have been an easy exercise. Questions on that? Again, the book has a theorem. They state this. I'm saying, okay, good. That comes from what you already knew, is all I'm saying. If you want to memorize that theorem, hoorah. Otherwise, if you know how to write an equation line, you're there already. Questions? So y'all figure out how to do it on the lab. Let's ask that. Figure out how to write the equation with tangent line on the lab. Someone, yeah. So, what about the normal line?
Yeah.
Sure.
How do you do the equation with the normal line?
Sure.
Now, again, it's not in the book. This time, you can't look it up in the book because it's not in there. I expected you to remember something from algebra. If two lines are perpendicular, what do you know about their slopes?
They're opposite. Reciprocals.
Yes, the negative reciprocal. So with that in mind, the normal line, you're going to still use the same order pair, but what slope are you going to use? Instead of f prime of c, you use -1 over f prime of c. Okay, that wasn't too bad. I think we got that.
Yeah, it wasn't.
Good. Local linearity. This is linearity, what we call differentials, is coming up next. Before I hit that, I'm gonna skip ahead a little bit to Leibniz notation versus Gauss notation. And the Newton notation. Question? Yes.
Who made calculus? Was it Newton or Leibniz?
Yes is the answer.
Okay. I'll take it.
What's the answer?
He's just said yes.
The history is that Leibniz published his work on calculus before Newton published his work on calculus. Leibniz is German, Newton is English. But once he published, Newton decided he was no longer afraid to publish He had been afraid for various reasons, including the church and all, because Galileo was already in trouble with the church for having said what he said. So Newton was a little bit afraid, but once Leibniz came out and published, because, Martin Luther was over there changing things, then Newton wasn't afraid, so he published. And he brought out his notebook to show, look, I had my notes years before Leibniz did his thing. And so they went to a trial, not a judicial trial in terms of legal, but it was the
This is about to get really intense.
Scientific Society of Britain, or whatever. It was the scientific body of the world at the time. And Newton and Leibniz presented their cases. Of course, it was run by the Brits, so we can think more about that in the court. So Newton got credited with it, although some people still say Leibniz should be, but we recognize both.
Neat.
Leibniz used this kind of notation. Newton is this kind of notation. Gauss introduced what we've been using.
Gauss? That's one of these is not like the other.
So all of those notations should be at least a little bit familiar. Most people don't use Newton so much anymore with the dot over the top, y dot, y double dot for the second derivative.
That's nice.
The Gauss notation is very convenient because it's really easy to say, if I want to evaluate the derivative at x equals 7, then this is real convenient because you just say, well, f prime was 7. That's easy. But how do I do it with Leibniz? That's a little more cumbersome.
It is.
To write the same thing here, you put dy by dx. That's how you read that, dy by dx. You evaluate it at x equals 7.
X equals what? Oh, wait, what?
dy by dx evaluated at x equals 7. That notation you need to become familiar with because you'll see that again, and especially if you progress further in, like if you take differential equations, you see that kind of notation all the time. Get familiar with that kind of notation. So they have their pluses and minuses, both of the primary notations we use. The Gauss notation is very convenient for saying, evaluate the number 7 in my derivative function. That's very convenient. Leibniz notation is very cumbersome for that, but Leibniz notation is very nice because what is it? That notation looks very close to delta y over delta x, which is the whole basis of the definition of width. So, I mean, this, to me, is very intuitive in the sense that if you put limit delta x goes to 0 of delta y over delta x, these two kind of look similar, dy and dx. These are d's, and those are what we call differentials. They're not deltas. But so this symbol is a single symbol that means the same as f prime. Delta y and delta x are two separate entities, so that literally is a fraction that you can multiply both sides by or whatever. This is a single entity. It's not a numerator-denominator fraction like that. Other ways of saying this, using the Leibniz notation, we have what's called an operator.
Operator. How can I help you?
So, derivative with respect to x of f of x is equal to f prime of x. So this notation here, you read it as the derivative with respect to x of the function f of x. So let me do that to you again. Derivative with respect to x. Now,
Respect.
oh, like Aretha, Aria, ESP, respect.
Oh, yeah, that's a good.
Well, this isn't because x is being disrespected, and we want to make sure it doesn't get disrespected. This is because as you progress further, instead of having a function of one variable x, we might have a function of two variables, x and y. We might have a function of 7 variables, x, y, z, w, a, and b. And then when you start doing derivatives of these multivariate functions, then you are going to need to know which one you're doing the derivative with respect to. For now, everything is just with an x. So saying with respect to x is redundant. But for the future, you need to know which one you're doing with respect to. Now, I can have derivative with respect to y of the function f of x, y, and z. That's calc 3. Or I can do that in here, but I'm just telling you why we say this is with respect to x. Again, it's not about dissing x. It's what variable we want to be focused on. Okay. Further up here on Leibniz, Gauss, we can have a second derivative of f double prime of x.
Double prime. Prime.
F triple prime of x.
Oh crap.
B derivatives. Oh my gosh, you can have more. If you go past the third derivative, putting primes gets messy because you put like. If I was going to do the 7th derivative, you'd put 7 primes. So that's real messy and awkward. So once you get past the third, then we put in little parentheses. But again, that's not f to the 4th power. That's the 4th derivative of f with respect to x.
Can you zoom in, please?
Pardon me? Zoom in?
Oh, sweet. Still can't see it. Just a little more? A little more? A little more? You're almost there. Please. Okay. Almost. Okay.
See it now?
Thank you. Yes.
Second derivative has 2 primes. Third derivative, 3 primes. Fourth derivative, we quit using primes and put a 4 with parentheses. And then so on. Fifth derivative is parentheses. On Leibniz, you can have second and third and so on derivatives as well. The notation for that is, you're going to go to the second derivative, you do the second derivative of y with respect to x.
Oh my gosh.
Or you do the third derivative of y with respect to x.
Why does x get squared?
Oh, that's a 3 on the x. Sorry.
Why does it get to get... Why is x going to x different? Mr. Gaddis?
That's right. Yes?
Why
Yes.
is the x...
Oh, you can't see me. I'm over here. Yes.
Why is the exponent on the top different from the exponent on the bottom?
Well, first of all, it's not an exponent, Razel.
Is it the prime
It's not
thingy?
it's not squared and it's not cubed. That's the second derivative.
Yes. But why is it written differently?
Question. In this, because we're thinking of this as, okay, let me go back to this notation here. So I can write that with an operator, y by dx is equal to the derivative with respect to x of y.
Okay.
This symbol is the name of a function. This is the function you started with, and this says do the derivative of it. Are we with this? So this is, we call this a meta operator. Instead of adding or subtracting, it's an operation like a function. It says do something to that function. It says do the derivative of that function. And then we name it this. Or we name it that. Name, operation. So,
Yeah, I'll take it. Keep on going. I'll take it.
so what if we did the derivative twice? So we would do the derivative of
Oh crap. Oh crap. Because that's the earlier function. So if you're taking the derivative of a derivative, you got a double derivative.
So that's why the.
Why
So
would
now
you
you have a double derivative. This
It's
is doing the
because of
derivative
That's
of a
why.
derivative. So that's the second derivative
Oh my gosh. How could you leave
with
this?
respect to x of y. So we're doing the second derivative of y, but now we can just take that y and put it up here, and that's why that y stayed the exponent. The superscript that indicates the derivative level
You
looks
want me to call
different.
it superscript?
Yeah,
I'll call it
superscript.
superscript.
A superscript is just a location that we use for exponents. Exponents have no special meaning other than we assign meanings to it. Superscript is used for exponents. It's also used for derivative, other things. Okay, so that's notation.
Say his name. Brittany, ask your question.
Mr. Gaddis,
Question? Yes, Britt.
why would you want to take multiple derivatives of a function?
That's a good question. What did we just explore in the position function? The first derivative showed us velocity. The derivative of velocity, which is the second derivative, showed us
Acceleration.
acceleration.
What's after
The
acceleration?
first derivative of position.
Someone get a physics teacher.
Physics teacher, right? On the chart. It's how fast you snap that acceleration. And then you can go past, I don't know the names of those after you go to the third one. But if you have a physics instructor, they can explain to you what the fifth derivative means in terms of Einsteinian relativity or something like that. So, from our standpoint, theoretically, we just look at it as each derivative tells me the slopes of the tangent lines of the previous function. So if I'm given f of x and I take the derivative, that derivative function tells me the slopes of all the tangent lines on that function. If I take the derivative of that, the second derivative tells me the slopes of all the tangent lines on the derivative function.
Yeah. I got it.
Follow
I
that?
got it.
So each derivative is just simply telling me the slopes of the tangent lines on the previous function.
Mm-hmm.
That's just purely theoretical. And in terms of physics, well, I'm going to stop at third derivative of jerk because I don't like being more of a jerk than and I honestly I don't remember what the fourth derivative is called. It's a lot of physics. I think it looks like we're backing up, so it must be getting close to out of time. It's actually past. It's right at time, 9:05. Okay, so we will stop here today. You need to go ahead and continue working on section 2.2. There's a homework listed on Moodle. I think it's every other odd exercise, something like that. If it goes all the way through, as much of it as you can, and we'll continue tomorrow with some more content.
Brittany, we need to build a bridge.
It's called Snap
Now, you look
or
it up.
Down. Say you Google.
Google.
Okay,
Hey, y'all hear that over there? Great stuff.
Yes.
Did you hear that? We
What did she
just
say?
Googled fourth derivative is called snap
Snap or Jounce
or
Snap or
jounce.
jam?
Jounce
That's awesome.
with a J.
with a J, jounce. Can you fit?
Let's get some caffeine. Let's get some
Derivative of a function. Would
Oh, I
that
have one. I
be,
just-
the slope would be original function?
No, it's the slope of the third
But it's like the slope of the slope
Of
of
the
the
slope
slope
of
of
the
the
slope.
function.
Yes,
So
Carson.
isn't that one of the slopes?
Dang it,
Wouldn't that
Carson.
just be one of the slopes?
forgot to get your
of the
shoes.
equation?
What?
I forgot to get your shoes.
I don't
Dang
know
it.
how to
Why do you
ask.
gotta
I don't yell his name like I do.
This is yours. Why am I?
Ask so that people understand what I'm trying to say.
forgot to bring your shoes. Yeah, I can't get them clean. Just throw them in the washing machine or something. I'm not putting them
Find
on.
some time.
I don't have a spare, what is it called? Pillowcase. I was thinking about bleaching them, but that's too risky.
I think I've got
Yeah,
one
I do.
first that.
I don't know.
What do that I trapped in
I mean, that makes white yellow.
I have
Does
the
it?
only pattern socks I have are donut socks.
I don't want to make your already
I have a lot
off-white
of
shoes
pattern
yellower.
socks, but they're Christmas socks.
That's nice. I like Christmas. Okay, let's get this deleted.